We're moving on to section 3.4 now, solution calorimetry. So this is a bit more formal and a way to look at reactions that occur in solution and how we can measure the enthalpy of reaction there. So we could have, because it's in solution, we could have an endothermic or an exothermic reaction. But definitely, whoops-a-daisy, let's go back, definitely in solution. So I've just used a little subscript there, RXN, which means reaction. So delta T reaction is the change in temperature of the reaction, of the water during the reaction. So the actual reaction's happening in the water, so it's actually the water surrounding the reaction. Okay, so calorimeters are definitely an improvement on just burning a bit of fuel under a grotty can, but the most important way in which the calorimeters are an improvement is not just because they've got a lid and they've got insulation, but that we calibrate calorimeters. So calibration is about matching a value to a reading. So we're matching energy to the temperature change. So in our calibration, we take a fixed amount of energy, we add it to the water, usually electrically, but not only, and we measure the maximum temperature change that occurs as a result of that energy going in. So we're relating energy with delta T, and that's our calibration. So we must make sure that everything else about the calorimeter stays the same during calibration. So we need the same water, we would need to use the same thermometer, we'd need to, of course, use the same calorimeter. You wouldn't want to be swapping and changing. And we need to use the same, I said thermometer, so I think that's everything. If we, just as a sideline, if you had 100 ml of water in the calorimeter, because our calibration factor is related to the specific heat capacity times the mass, then we would end up with a calibration factor of 418 joules per degree Celsius. So that's what you'd normally expect for 100 ml of water. Sadly, we tend to see values below that due to the calorimeter itself, the insulation, absorbing heat that's released. So, as I said, calibration is needed so that we can relate specifically the Q to the change in temperature, because otherwise the Q equals MC delta T is not taking into effect that we've got some insulation and there's going to be heat absorbed, but also that we're not losing heat to the surroundings. So it's a win and loss, but mostly we win when we're doing this. So the calibration factor takes everything into account and is usually pretty consistent across all temperature changes in the calorimeter. So we might use Q or we might use E for energy as we go ahead. So don't be confused. It's just me jumping around a bit with Q versus E. So electrical calibration, first of all. So this is when we pass electricity through a wire and the wire is in the water that we're trying to heat. This is how old kettles used to work. They used to have an electrical, let's just call it a wire because I can't, element, there it is, an electrical element that was a very high resistance, and so it would give out a lot of heat, and so you'd pass your electricity through the wire, and that's being shown here by this rather strange looking device. It's probably more reasonable to represent the wire like this. So these are coils of wire, and as the wire gets hot, the heat goes out into the water. So we need to know how much energy has gone through that wire. So we've got a new value here, which is going to be very useful later. And that's E equaling V times I times T. And I'm not quite sure why I'm rewriting that when it's there, but never mind. This could also be Q if you preferred. Q equals V times I times T. Most importantly, V is voltage that you would read from your voltmeter. I is current. So I and current are the same. Just be careful there, because a lot of people think maybe we've got C for current, but we've already used C. That was specific heat capacity. And T is the time that the current is passed for. So when we're using a calorimeter, we can plot the change in temperature on a temperature time graph. And this enables us to evaluate the insulation of the calorimeter. So a calorimeter with poor insulation is going to lose heat after you turn the heater off. So in these graphs, we've got current being turned on at this point and turned off at that point. So 240 and 120. So the current is on for 120 seconds, 2 minutes. In your experiment, you're going to do it for 3 minutes, but that's later. That'll be after I come back. So we turned on the current going through the wire heats the water, the temperature of the water goes up, and then we turn off the current, and then we know the time. So time was equal to how long the current was turned on. V was the voltage that was being shown while the current was on, and I is the actual current. So you would have a voltmeter and an ammeter for reading the voltage and the current. Once we've got those results and we've plotted them, so this is once again where our data logging is absolutely fabulous, then we look at the quality of our graph. Now, if we've got an absolutely perfect graph where the temperature does not change after you turn off the heater, and it did not change beforehand, then your change in temperature is simply the highest temperature minus the lowest. If the temperature either continues to increase after the heater's turned off, or if it drops down, as shown here, you're going to have to extrapolate. So you draw a line of best fit and you extrapolate all the way back to the point in time when the heater was turned on. And then you've got a larger delta T. If we think why we're doing this, the line of best fit is sloping downwards because heat's being lost. So your argument is if heat was being lost after you turned the heater off, you've got to assume it was being lost while the heater was on as well. So that's why we do it. We're allowing for the heat being lost along the way. Okay, so when you've got a calibration, then we can make when we've done a calibration, you can create a calibration factor, shortened to CF. And its units are joules per degree Celsius, because we've got the joules that we added here, and we're dividing it by the change in temperature. So this, now you'll see maybe why I started using delta T of reaction, because we've got 2 delta T's sitting here on this slide. Very frustrating, very confusing. So 1 delta T was during calibration. So that one is during calibration. And you work out the calibration factor by dividing the energy added. So that was your V times I times T. And then this one is delta T cal. So VIT over delta T of calibration gives you the calibration factor. Then you multiply your calibration factor by the temperature change when you do your reaction in the calorimeter. So this is when the reaction is complete. So this is a separate experiment after doing the calibration, and you get this value delta T of reaction. And so then we can work out the energy, and then all we have to do is work out delta H. So working out delta H is going to be the energy of reaction over the number of mole. And that's a few slides in advance. You'll see it shortly. So here's an example of our electrical calibration. So we have I. Don't forget to annotate your questions so that you know what values you've got. We've got a number of seconds, T, and we've got our voltage, V. And the temperature change is worked out by subtracting 18.05 from 19.38. So we put our values of V times I times T into the equation E equals VIT, and we get a value in joules. Delta T is the difference between the initial temperature and the final, and it will always be a positive value. Remember, when you need to show that the reaction is exo or endothermic, you need to use the sign just as the code for exo and the negative sign for exo and the positive for endo. So if this temperature, ignore that, because this is electrical calibration, we're putting energy in. Apologies, it's Sunday afternoon, what can I say? So we divide our energy by the change in temperature, and that gives us our calibration factor, which, as I told you earlier, is a little bit under the perfect value of 418. All right, you've got to try yourself. So have a go at that example, stop the video and mark your work, and then come back to me. All right, another way to calibrate a calorimeter is to do a reaction in the calorimeter. So you don't use the heating coil, you don't use an ammeter and a voltmeter and a power pack. You use a reaction to put energy into a calorimeter. And so you need to know delta H for that reaction. You need to know the mass of what you're putting in so that you know the mole. And then you measure delta T. So this time, the energy added during this chemical calibration is worked out by taking the number of mole and multiplying it by delta H. So the energy is the number of mole for the calibration constant times delta H. And then we work out the calibration factor as we did before with calibration energy divided by delta T. So in this worked example, we're working through all of that. Here's our mass of the potassium nitrate for calibration, and that's going to be turned into mole. We've got the molar mass, so we can do that. We've got the volume of water, so we've got the mass of water, and we know the delta H, and then all we have to do is we measure the temperature of the water, and we've got quite a big drop, 20.5 down to 10, and away we go. So work out the moles, multiply the moles by the delta H of the substance you're calibrating with to get the energy that, now it actually didn't go into the calorimeter here, it was absorbed because this is an endothermic reaction. So this gives us a bit of variety in our lives. Got an endothermic reaction. So the change in temperature is the highest temperature minus the lowest. So that's 10.5. But we are noting that the temperature has gone down. So we're very, very aware that this was endothermic. It's all working fine. We don't really have to do anything with our calibration factor here. We just use the endothermic reaction. So we took our energy in kilojoules, divided it by delta T, and we came out with 492 joules per Kelvin. So possibly your calorimeter is working better with the endothermic reaction than it would have with an exo. So there's food for thought. Okay, try yourself. Do this example. Stop the video, of course, and then correct your work from the back of the book for worked example 3.4.2. Okay, so once we've calibrated our calorimeter, whether it's by adding electricity or doing a reaction in the calorimeter, then you're going to use your calibrated calorimeter to perform a reaction and measure the delta H, or find the delta H. So this time you need to know the amount of reactants that you actually used during the reaction. So remember, this is a different day even. It could be that you've got your calibrated calorimeter and on the day after you're going to use it to measure the enthalpy of reaction. So we need the amount of reactants that we're putting into the reaction, into the calorimeter. We need to measure the change in temperature, and then we are going to work out that energy of reaction is equal to calibration factor times delta T of reaction. So this is the second time I've mentioned this. And then our delta H is going to be the energy of the reaction divided by divided by amount in mole. Okay? And when you're writing it into the equation, that delta H is for just 1 mole. So if your equation is for more than 1 mole, you might have to double it or increase it. So chance to do the calculation. So we've got our calibration factor here. We've got the delta T for the reaction. We're adding some glucose. So we've got a molar mass and a mass, so that'll let us work out N, and away we go. So we work out the moles of the glucose and it comes out to a very perfect 0.0500. We multiply the change in temperature during the reaction by the calibration factor that we were given in the question, and it's 0.550 kilojoules. And now divide the 0.550 by the amount in mole of the glucose to give us 11 kilojoules. And because the temperature decreased, we were told that in the question, then it's a positive delta H. Positive 11 kilojoules per mole. All right, one for you to try. This time it's sucrose, not glucose. So try yourself, stop the video as always, mark the work. So here we have all the formulas. Hopefully this will be something handy to be able to refer to. So these should go into your summary, of course, but remember, many of these would be given to you. Many, but not all. The one that wouldn't be given to you would be this one, and maybe that one. I'm not sure. Hang on, if only I had a dark book. Here we go. Q equals MC delta T is in the data book currently. Calibration factor is equal to VIT on delta T. That's in there. And enthalpy of combustion equals Q over N. So that's in the data book. That one was in the data book as VIT. And Q equals MC delta T is in the data book. Okay, that's handy. So that's the end of section 3.4. Please do the questions as you're going along. So do questions 1 to 7 now for 3.4. And that's the end of this video.